Welcome to this lecture series in number theory. In this lecture, we'll look at some applications of Bezout's theorem, but those applications will also draw upon some things we learned previously. So Bezout's theorem has been stated here, and we learned some properties of GCDs in the previous lecture. They were non-trivial, but I have collected them here. Some of them, I think I missed the associativity, but okay, that's fine. And here is the Euclidean, or the key fact about the Euclidean way of computing GCDs. Okay, so I have written it over here. Okay, fine. So these are some bits and pieces that we will make use of. Some problems for practice. And now let us get started. So our first application will be a very standard one. You must have seen in high school that root 2 is irrational. But what does that mean? It means that there is no rational number whose square is 2. That's what it means. Because when you write root 2, it's like it's some number, which it is if you know about real numbers properly. Right? There is a real number genuinely whose square is 2, but that's not an easy fact because real numbers are not an easy object. They are pretty sophisticated. At any rate, this statement makes sense within the realm of rational numbers. We are saying that fix a prime p. There is no rational number x whose square is p. If p were equal to 2, very simple proof can be given, but when p is some arbitrary prime, we need some theory, which we have already developed. And now let's see why. In fact, I encourage you to pause the video and try to solve this yourself, as with anything in this entire lecture series or in any lecture series. At least spend some time with this statement of any theorem or lemma, so as to get a feel for what's to come. Otherwise, you just become a passenger. Okay, all right. So let's see why this is true. We will approach by contradiction. So assume on the contrary that there is some rational number such that x square is equal to p. Okay, and we may assume that x is positive. That much is fine. And let's say if it is a rational number, you can always express it as a ratio of two integers. So say x equals p by q. I don't want to use p. Let's say x equals a by b, where a and b are positive integers. A and b are integers, but they are also positive. Any positive rational can be expressed as the ratio of two positive integers, but more importantly, we may also assume that a and b are relatively prime. So that's the crucial thing. May and will assume that a and b are relatively prime. Any rational number can be expressed as the ratio of two relatively prime integers, because if there were a common factor between a and b, you can just cancel that common factor out. Okay? So far nothing has been done really. It's just the natural steps once you go via contradiction. Nothing has been done. But now we use the fact that, we have let's exploit what we have assumed to be true. So now, since x square is equal to p, we get a by b whole square equal to p, which if you cross multiply, you get a square is equal to p times b square. Okay? Which in particular means that b square divides a square. Right? But this implies that b divides a. Or, in fact, I will say it in a different way. By what we learnt in the previous lecture, if a and b are relatively prime, then a square and b square are relatively prime. Okay? This we learnt. Any power of b and the same power of a. In fact, you don't need the same power. You can take any positive power of a these two numbers will be relatively prime, right? But now, at the same time, we have b square divides a square. This implies that b square is equal to 1. So let me write the reason for it. Since a and b are relatively prime, by exponentiation property, which we recalled in the beginning, we have that the GCD of a square and b square is 1. And the rest is clear. Once you know that the GCD of these two numbers is 1, and at the same time this one divides the other one, the divisor should be equal to 1. That is clear. Which implies that b is actually equal to 1 because b was positive. Okay, so what does that mean? It means that x is actually an integer. So x is a positive integer with x square equals p. But p is a prime. It does not have non-trivial divisors, while x square has non-trivial divisors, namely x. Right? X divides x square, but x square is p, and hence the only possibilities for x are 1 and p, because x is a divisor of p. The only possibilities for x are 1 and p. But if x equals 1, then p equals 1. 1 is not a prime. If x equals p, then p square equals p, which again means p is equal to 1. Because you can cancel off p from both sides. So that's it. Either way we get a contradiction, and that settles this. So this part of the proof is where we are making use of non-trivial properties of GCD, and arguing this without all those properties or arguing this directly is tricky. If p were equal to 2, you could get by, but for some arbitrary prime, I believe some sophisticated reasoning is required. All right, so this is done. I mean, I'll put a dot here for you to fill up the details, but this is fine. So let's move on. And this is a very interesting puzzle. It asks us to prove that there exist arbitrarily long non-constant arithmetic progressions, which I will explain the meaning of, with the property that any two terms of this progression are relatively prime. So, for example, first let me define what is an arithmetic progression. So, an arithmetic progression of length L is a sequence. And here when I said arithmetic progressions, I meant arithmetic progressions of integers. We are only dealing with integers because we are talking about relative primality. So an arithmetic progression of length L, but when I said arithmetic progressions, I meant arithmetic progression of integers. Yeah, so of length L is a sequence A1, A2, AL. In our case, these are integers, but they could be real numbers in general of integers such that the successive differences are constant. Right? This is called a non-constant progression if they are different. If all of the numbers are same, you call it a constant progression. That's not much of a progression, but it is technically one. Okay. And for example, you can take 3, 5, 7, 9, and so on. This is an example of an arithmetic progression. But if you want it to be of certain length, this is an example of a length 4 arithmetic progression. The successive differences are constant. They are all equal to 2. Right? But this is not an example of a length 4 non-constant arithmetic progression with this property, because 3 and 9 are not relatively prime. If I had stopped here, then this would be a length 3 arithmetic progression with any two terms being relatively prime, But as soon as the fourth term comes into existence, the relative primality breaks down. Okay, wonderful. Yeah, so I hope the puzzle is clear, and it should be very interesting. You should be able to appreciate that the beauty of the puzzle. Okay, so as usual, I encourage you to pause the video and think about a solution. So let me try to explain how are we going to go about this. So suppose we want to produce an arithmetic progression of length, let's say some length n. Then we want to produce a sequence of this sort. The first term we may call a, the second we may call a plus d for some non-zero integer d because we want a non-constant progression. The third would be a plus 2d and so on up to a plus n minus 1 to d. So these are n terms in arithmetic progression, and generically any arithmetic progression can be written this way clearly. So we just are constrained to choose a non-zero integer because we want a non-constant arithmetic progression. This d cannot be 0. And what do we want? We want all of them to be pairwise relatively prime. Any two terms in this progression should be relatively prime. So we would like to have that, the GCD, so want the GCD of a plus kd and a plus ld, where k and l are different. We want this, and it's unclear how to achieve this. There may be many ways of doing this, but I can do it in one way. Fine, so this is what we want, which is equivalent to wanting by Euclidean theorem or whatever. This is same as asking that the GCD of a plus kd and this number is 1. So what did I do? Call this alpha, call this beta. We are just using the property that GCD of alpha comma beta is same as GCD of alpha comma beta minus alpha. This is by Euclid. So if you use that, showing that this is equal to 1 or asking for this being equal to 1 is same as asking for that being equal to 1. So we would like that this be relatively prime to that whenever k and l are different. Okay. So how do we achieve that? Well, yeah. So we want to show that this is relatively prime to that. And again, by what we learned by the clubbing property, if we can ensure that this is relatively prime to that and this is relatively prime to that, we would be done. So that could be a strategy, and let's see if we can employ that strategy. So it's quite easy to make this relatively prime to that. Why? Because just to take a as 1, that would ensure that this number is relatively prime to that number, because GCD of 1 plus kd and d is 1. This is clearly 1. You can use Euclid or you can use common sense. If you have a common divisor of these two things, it would also divide 1 plus kd minus kd. Any common divisor of the two numbers will divide this difference and blah blah blah. So it should be clear that if a were chosen to be 1, the GCD of, the number d will be relatively prime to this number, where d could be anything non-zero. So we would like to also make this relatively prime to that after we have chosen a is equal to 1. Can that be done? I don't even know if that can be done, but let's see. Yeah. So L minus k. So L minus k is a number. L minus k is a number which is between 1 and n minus 2 or something like that. So it has some range. And if we choose d cleverly, then we can even ensure that this is a divisor of d. And that will be the strategy. So here, so that strategy will work. We will choose a as 1 and d suitably so that this becomes relatively prime to that number. and that will be it. So here is the proper proof now. So fix n greater than equal to 1 or n greater than equal to 2 because we want to produce a progression, not just one number. So now we will produce a progression, an arithmetic progression of length n such that any two terms of this progression are relatively prime and that this progression is non-constant. So choose or define d as, I think n factorial should do. Let's see. Yeah, I think n factorial will be fine. What is n factorial? Remember, n factorial is n times n minus 1. Correct? And now the progression is, so consider the numbers 1, 1 plus d, 1 plus 2d, up to 1 plus n minus 1 into d. These are n numbers and we claim that these are pairwise relatively prime. Right, so why is that? So to do that, let K and L be chosen this way. Then the GCD of this number where A is 1 and that number, we want to show this GCD is 1. But by the Euclidean thing, this is equal to that. But L minus K divides D. L minus K is a number between 1 and n in particular, right? This in particular implies that L minus K is like this. I mean, one can say better, but this is certainly true. And any number in this range divides n factorial. So L minus K divides D, and hence it is relatively prime to 1 plus KD. Right? So note that L minus K and 1 plus KD have GCD 1. And almost by the same reason, this is also 1. D divides D and hence GCD of D with 1 plus KD is 1. L minus K divides D and hence the GCD of L minus K with 1 plus KD is 1. Now we use the clubbing property. By the clubbing property we get that. I'll write it. GCD of 1 plus KD L minus K into D is equal to 1, which implies by the previous observation that GCD of 1 plus KD and 1 plus LD is 1. That's it. That finishes the proof because K and L were just arbitrary. Very nice and short proof and very well motivated. It's not like we pulled this number out of a hat. We had a fairly follow your nose kind of argument in some sense. All right, so one last thing for today. This is also very interesting. We have three numbers, both, all three of them positive integers. We want to show that the GCD of this number and that number is very interestingly this number. So the power is just replaced by the GCD. It's quite strange that this is true. And again, pause the video and try to solve it. All right. So we will use G to denote the GCD of A and B just for brevity. Okay, and one thing we can immediately note. Note that this thing divides both these numbers. Now, why is that? Well, it's very simple. It's just that if you call, the reason is, say, A is equal to D times alpha is some integer, then, and say n to the power A is M, then n to the power, sorry, not n to the power A, but n to the power D, or rather G. So this was a G, not a D. There is no D. So n to the power G is denoted as M. Then n to the power A minus 1 is m to the power G minus 1, which is, you must know, m minus 1 times correct? We have that. And what is m? M is n to the power G. N to the power G minus 1 is dividing n to the A minus 1. It's a very simple thing that I'm saying, but I said it in full detail. So I hope you follow that these two things are there. And thus, from this observation, thus, the GCD of these two numbers is at least this number. Right? We want to show equality, but we have at least made some progress. Great. And now to do the full thing, note that for the reverse inequality, we have that this GCD is, by the Euclidean thing, I hope this is clear. Call this x, call this y. All we are saying is that GCD of x comma y is GCD of x comma y minus x. Right? This is the Euclidean thing, which is equal to this thing, which is also equal to, if we pull out the common term, so we pull out n to the power A, right? And here I would like to assume that this is an integer. So we may assume that B is at least A. This is not assuming this is without loss of generality. So this is fine. But now note that this number is relatively prime with that number. Right? Any number is relatively prime to the number just previous to it or just after it. Right? N is relatively prime to n plus 1 and n is relatively prime to n minus 1. So you can use the dropping property to say that this is equal to, right? This is where we use the dropping property that we recalled in the beginning. Okay, great. And now if you just focus a little bit or maybe zoom out a little bit, you see this is in some sense a Euclidean algorithm happening in a slightly convoluted way. If you ignore all these decorations, what do you have? You have the pair A comma B, and then here what you are left with is the pair A comma B minus A. And you can keep applying the same reasoning. You will keep subtracting off from the bigger one. At some point you will end up at GCD. One of these terms will be n to the power G minus 1, or let me explain that by some example. So suppose we are dealing with 6 and 14. So so GCD of n to the power 6 minus 1 and n to the power 14 minus 1. We want to show that this number is n square minus 1, because the GCD of 6 and 14 is 2. Yeah. So what have we done? So by the first step of the above procedure, we would get, this is n to the power 14 minus 6 times, this would be n to the power 14 minus 6 minus 1, right? That's what this equation gives us immediately. But 14 minus 6 is what? 14 minus 6 is 8. Now, one more step of this reasoning gives us that this is GCD of that, correct? Which is nothing but n square minus 1, which is at most GCD of, which is at most n square minus 1, right? Because this number is appearing here, and the GCD of two numbers cannot be bigger than any of the participating numbers. So we have that the GCD of these two numbers is at most n square minus 1, but the other inequality is anyway clear, as already argued in this step. So what I'm saying is that the phenomena that happened here happens in the most general setting. You keep applying this reasoning. If b minus a is still greater than a, you apply this one more time, right? And keep sucking out from b as much as you can, right? At some point, either one of these numbers will be equal to the GCD of a and b. If not, suck out from the bigger number. You again subtract. And at some point, one of these two numbers will become n to the power GCD minus 1, at which point you can declare that the GCD is at most n to the power g minus 1, and you will be done. Right? I hope this reasoning is clear. It's important to follow this. Okay, and I don't want to say anything more because saying more will only confuse. So with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.